السلام عليكم ورحمة الله تعالى وبركاته. معكم ناوي أحمد من برلين ألمانيا، واليوم سوف نتحدث أو ضيفنا الدكتور سعد ياسين من كندا، وهو President of the International Ozone Association, and he is consultant also in Windsor in Canada. He will talk about a very important topic, and not only important but very vital for the humanity, and especially in countries where water is missing. That's why in his title there is scarcity of water. So the title of his talk is Water Reuse, a solution to water scarcity and sustainability. Dr. Saad Yasim, I know him since many years. We met together in Qatar, in Doha, in Qatar Foundation. We worked together. We had a lot of time together. We discussed a lot about environment, and he's very much concerned about the environment. Actually, he's the president of the International Ozone Association. He was, as I told you, former acting research director at Kiri and joint professor at Hamad Ibn Khalifa University at Qatar Foundation. He's a consultant, environmental consultant, and founding CEO for the Wilkerson Clean Water Center following the outbreak tragedy. Maybe he can tell us better about this outbreak tragedy. It's very important. He introduced ozone, a highly reactive gas, as primary disinfectant to the city of Winston in 2001. Designed a water reuse system for greenhouse operation in Canada. He was also an adjunct professor at the University of Winston, Canada. And of course, International Ozone Association Harvey Rosen Award for 2009-2010. So you are in front of an expert in the water treatment, water reuse, and he will give you a lot of detail and about this technology and the state of the art. Dr. Saad Yasim, thank you very much for being with us. Thank you very much that you are willing to give as member of the virtual learning university, you want to give a course, and maybe by the way you will explain your syllabus at least orally or with PowerPoint, whatever. And the floor is yours. Thank you very much. I will leave now the screen for you.
Okay. Thank you, Dr. Ahmed. And
please go ahead.
I'm going to share the screen. You see my screen?
Yes.
Okay. Assalamu alaikum. Thank you, everybody, for being here today. The topic is water reuse, a solution to water scarcity and sustainability. Water is a topic that I've been working on for the last 30 years. And because life do not sustain without water. The thing is, as we know, the issue of water problems differ from one area to the other. My focus here is going to be on the Middle East and North Africa, which is the MENA region, and the Arabic countries, because that is what our focus is, because the challenge in that area is different from the challenge in Europe and North America and other places. As we know, there is a lot of development has been happening in the MENA group in the last few years. A lot of work in desalination, improvement of infrastructure, dams, improvement of drip irrigation. However, there are some challenges to optimize the management and maintain a system that will be sustainable on the long term. So most of the time, the groups in MENA region has focusing on the conventional way of looking at things to have a drinking water from the existing sources and providing that, which is good. But with the water scarcity and increase of population, urbanization is becoming a world problem or a global problem because many people are leaving the remote and village areas into the cities. So what that means is more load on the drinking water system and the sewage treatment system. And what does that mean is more stress on the water resources. The Arab countries covers about 10% of the area of the world, but receive only 2% of the world's average annual precipitation, and contain as little as only 4.3% the global annual renewable water resources. What does that mean? Because the water is a cycle. I like a video one time made by the American Water Works Association, and we use that for training, for education to children, grade 4 and 5. They used to come to the water plant, we show them that. They show them the video, a cartoon, tell them this is the same water the dinosaurs used to drink. So it's a water cycle. And I remember one of the students became a graduate student, and she was telling me, I still remember that video about the water cycle. And she joined the environmental engineering and went to do her master's because she got interested in the issue of the water cycle and how can you maintain it. The rainfall, annual rainfall, usually in the Arab region is low, around 250, but that's different regions. In some places, it's only 5 millimeter on annual rate. That is very low, it comes. We see in some locations there, when we have the flooding and rain in our area, we could have 50 to 100 millimeter in one day. So you see the difference. Surface water resources in the MENA countries, the volume, these figures I'm mentioning, it is from the World Bank. So that is what I got the data as an international group. 224 billion cubic meter per year. 77% of that comes from outside the region. And that could cause political issues. Plus, when there is a drought, the countries that have the original water system might control it by putting dams to keep the water for themselves and reduce the water that goes into the other countries. And we've seen it in a few countries in the Middle East. Desalinated water is a great successful operation, and using seawater. And we saw that in the GCC countries has been very successful. And however, the use is increasing, the demand is increasing dramatically. And what does that mean? Also, the salt produced from that is a problem if it goes back to the water as well, or even if you keep it in the land and water comes, so you could cause issues. Agriculture is the biggest use of water supply, and the consumers use almost 85% of the available water resources in the Arab countries for the agriculture. And but you have for countries like Egypt, Sudan, Algeria, Morocco, Syria, they contribute 71% of the total agriculture output. What does that mean? There is still a lot of agriculture import coming from outside the region. And with the water demand, many of the countries in the MENA region try to be more sustainable for food security by having more agriculture use. but that means is more stress on the water sources. Irrigation efficiency might not be as good as it should be. The estimate is about 30% compared to the world average of 45%. Also, we need to recognize that the agricultural sector only makes a marginal contribution to the national GDP, which is the gross domestic product. Like I lived in Saudi Arabia, I lived in Qatar, and I visited many of the countries in the region. We still import, a lot of the food, vegetables, fruits from outside, and that is could be an issue. And we see now with the increase of the cost for food products, vegetables, and fruits, it's increasing rapidly recently. And the water demand is expected to increase dramatically, and that means more wastewater is going to be produced. And the rapid urbanization is one of these the causes for that, because when you have an increase of water demand, basically you're going to impact your water sources, and that's going to impact the sustainability of your system. The average per capita domestic water consumption in the Arab region is about 400 liters per day, compared to about 525 liters per day in the United States. However, I'm not saying that's good. 525 is in excess. And we say it in conferences, and I use it in my lectures. We waste a lot of time in Canada, United States, of the use of water. People stand in the shower for half an hour. You don't need that. Compared to people in Africa, try to use water for just try to keep the sanitation in good shape. So, but the domestic water consumption is escalating. In 1995, by 12,000 million cubic meters to 16,000 million. So that is a substantial increase. That's about 30% increase. So that is, and the water resources is not increasing. This table provided by the World Bank, it shows they calculated the water withdrawals based on the desalination capacity, and they looked at the data that they collected in 2016. And if you look at the desalination, and you have the water reuse for agriculture, drainage water, groundwater sustainability, surface water sustainable, groundwater, if it's understood. So these colors, it shows the impact, and they put that per countries. And you see it's quite different in the region. And there are countries that struggling in that shape. And you see here, Libya, for example, it's a struggle. And you see the situation here, the groundwater is unsustainable. And it's a problem. And that thing is because, groundwater is a saver for when you have problems, when you don't have enough surface water after a drought. But the recharge of groundwater is a serious matter, need to be considered, because this will help the countries when they have major drought in their climate. And this is, you see here, the water withdrawals by source as a percentage of the total withdrawals by countries as well. And you see one of the highest withdrawals is Libya, again here, Djibouti, Saudi Arabia, those are the highest three. And the thing is, if you have surface water, it will be good, desalination, but desalination as well, you have to think about the user cost of energy, and the future expansion, because the cost of desalination is not low, and that's why you need to look at sources that cost less to provide water reuse for agriculture, for example, like the cooling towers and all that, because you don't need to use a treated water for that, drinking water type. So, and we've seen in some applications how useful that could be. Reclaimed water is a big step. People start to look at it seriously in different parts of the world. Municipal water system, they can treat the drinking water and retreat the wastewater, the treated sewage effluent, can be recycled and reclaimed. And this table here shows the categories for water reuse application. You have urban reuse, agriculture reuse, impoundments, environmental reuse, industrial reuse, groundwater recharge, and non-potable reuse, and potable reuse. The application is different from one region to the other. In the United States, in Singapore, there is a potable reuse. And our culture and our religion, people don't like to have that because there are some limitation and cultural and religious issues. So if we focus on urban agriculture, environmental reuse, industrial reuse, groundwater recharge, that would be great, because this is a small part compared to this. And that will reduce the use of the drinking water that we use it for these applications. And that will make a difference. And I don't want to go into the details here, but this table will be available in the presentation. And if anybody is requesting any more information, I'll be more than happy to provide them with the information. The problem, one of the problems I've seen worldwide is the weak baseline water quality regulations. The thing is, because the water quality regulation difference for gray water from the treated sewage effluent and for the use, because you need to know what is the water going to be used for. So developing certain water quality parameters for that. And that's a challenge the MENA countries face as well. And even in some countries, Europe is more advanced than that. North America is still working on that, like in Canada. There is still some gaps there in the United States as well. But it is moving. There is people are start to think about that, about the use of gray water, the reuse. And we need to think about it more seriously in the MENA region. And we have to think about, because the water quality, the wastewater in the MENA region is different from France and United States or Canada. Food security is a serious issue. The Arab states and the MENA region import about half of the food demand. And this is the main of the, and the MENA group is almost the main world imports of cereal. However, there is still importing a lot of grains from other countries as well. And that is an issue because, we could be self-sustained. We don't have to import more of these grains if we can do it in-house. But if the water shortages, that could be addressed by technologies. Climate change impacts water scarcity more significantly in the Arab countries and the MENA region. And we've seen the temperature increase. And I've seen it from experience. As I said, I lived in Doha, in Qatar, and in Jeddah in Saudi Arabia for a while. And I see the impact in summertime and the length of the high the air temperature is increasing, and that has been shown in the models that's been running. And that's what the United Nations now, the climate change report about try to control the applications and work so the temperature does not increase by 1.5 degrees in the next 10 years or so. And that is a dramatic thing because that will increase the drought and also will increase the impact on water resources. There will be more scarce water resources compared to what it is now. So we need to look at more water reuse schemes. Like if you listen to the report given 2 days ago by the two ministers of Germany and Canada, ministers of environment, about they're putting $100 billion over a certain amount of years to apply to deal with the issue of climate change. And that's why we should be working hard to utilize the support of the United Nations and the programs available to deal with these issues. And the economic impacts of climate change, they're looking at here, the World Bank, the impact from now to by 2050. And you see the worst impact is the Middle East. The Middle East is the worst impact. They determined that because of the type of policies, implementation, and the water scarcity. And if you run business as usual, now without any change, that's what we end up with here, minus 14%. And if you do an improvement, you reduce it down to almost 6%, minus 6%. So there is a dramatic change if you do that. So you see here the Middle East, and you see here the world. So and there's the difference you see here in North America, Western Europe, because they don't have the problems of temperatures increase, like they don't have the long temperatures periods like what we have in the MENA region, but it is increasing for them as well. However, not as much, and you need to accommodate this by reducing the impact, because increasing desalination, for example, that means more energy you're using, more carbon emissions, and also more salt produced. So if you go to water reuse, you're going to be reducing that because the energy used to produce recycled water is much less than compared to desalinated. And also, you reduce the need to go and spend major capital infrastructure as well, because you just need to upgrade some of your sewage discharge. So the successful and efficient reuse of treated wastewater, especially in agriculture, will depends on different strategies, because reliability of the reclaimed water as an alternative to source to groundwater in irrigation, that will be a big difference. I designed a system and we implemented it in 2004 for a greenhouse. It's a big greenhouse in Ontario in Canada, 14 acres. They produce tomatoes. And so they used to discharge 100,000 liters a day to the Great Lakes. And basically, they pay for this water. They pay that much. It's a city water or even groundwater. There is a volume they're allowed only to take. So, and also the discharge has nutrients. So the nutrients causing problem of the algal bloom, because the algae will be increasing with the nutrients. So all this are keys to think about. So when we did that system, we did a complete recycle. So they reuse a lot of these nutrients and reduce the amount of water discharge. And system been running for the last 17 years successfully. Many applications follow that as well. So total reuse is about 2.17 billion cubic meter per year. Egypt, Syria, Middle East, United Arab Emirates, Saudi Arabia are the largest users of the 75% of the region in total. However, with the increase of population there, the demand will be more. Irrigation is the biggest thing, and irrigation landscaping is being used a lot by that water reuse. The golf courses, and also the parks. And I remember hearing from people there, there is a smell, people start to feel it in summertime, because the treated sewage effluent, the regular treated sewage effluent, still has organics. And there is potentially some pathogens as well, because some of the pathogens, special viruses, could hide in the turbidity or the organic matters. So there is a smell. They find it in summertime when these parks are. They use treated sewage effluent to have that. So you need to improve the quality for health and also from a statistic issue as well. And it shows here the share of collected wastewater that is untreated or treated or reused. And you see treated and reused in total only 18%, treated and unused 25%, and untreated is 75%. So these figures make us think that there's a lot to do. Reducing this untreated and reduce the treated and unused by improve the treatment. So because people want to make to be comfortable with the reused water. So a lot of efforts need to be done. We need to from education and also to inform people what needs to be done. Most of treated water reuse activities are driven by water scarcity, and that's fine. And we need to look at seriously where are the locations that we could use this application. This table, that's one of the latest, came in from the GCC countries, but this town for 2014 to 2018. There is an increase in of the water reuse from 0.68 to 1.1 milliard cubic meter or billion cubic meter. And so 63%, that still means there's a lot need to be done. When you have 37% more, that reduces the impact on energy, also on water resources. So we need to look at these figures seriously. When we look at water shortages, water scarcity is still a problem in the MENA, and it will increase. The demand is expected to increase by 50%. And there are expected 12 countries, the report from World Bank says 12 countries in the Arab and Western Asia region have less than 500 cubic feet renewable water resources per capita. And that is alarming. What we see here, the water stress per regions, and that is on surface water. The biggest stress in the Middle East and North Africa, which is the MENA group, East Asia and Pacific, South Asia, and Latin America, Europe. So the MENA region, Middle East and North Africa, is the highest in water, surface water stress. And the variability per year also are changing, higher than anywhere else. And if you look at the percentage population exposed to high or extremely higher level of groundwater stress, and it shows the countries here. Oman is the highest, and you see the list of the countries Middle East, North of Africa, and you see that with the increase of population and the temperature use, and I think with Oman as well, because recently there's a major increase in tourism, and when there is tourism, there is more use of water. That means more publications, more people are coming to the area, and when you go to the hotels and all that, there's more use, swimming pools and all that. So that's why we need to look at seriously on that use. And this shows here the countries that impacted. So you see here, this is the GCC countries, all impacted. And North Africa, you have the biggest impact of North Africa is Libya, and still you have Morocco, Algeria is still at that level here. So it's not on the safe level. Egypt, they have better situation because of they have the Nile River and also by the sea. And but here you have more impact of the desert area and population locations. And this area is depending on the desalination. So as we indicated, the issue of agriculture is increasing, and with time, people are more going into more healthy diet. So they want to use more salads, more fruits, more that. And where do you get that? And you see, you go and look at it. Oh, made in USA, made in Singapore, made there, that, and you don't see much of local products. And I've been to different markets in the GCC countries and in the MENA groups as well. And I've seen that factor is used, like the imported is quite high. So again, the reuse is a significant role. It will increase that. I'm gonna move into some of the from the experience I had in Qatar, and I look at that. There is an increase of treated sewage effluent in the area, and the use of that for mainly the reuse for parks, irrigation, and all that. So it is increasing. However, treated sewage effluent will be increasing, and that's why we could utilize it for agriculture more, and also for agriculture that leads to food products. And when I was there, I had an agreement with the Ministry of Environment to do a project like that, but because unfortunate situation, I had to leave after a year and a half, and we could not, and the equipment was not ready at that time. And the project did not continue on this. So wastewater treatment, and I'm going to be here, we're getting into technical issues. The municipal water system, it has different things, mainly pathogens. You have BOD, the COD, biological oxygen demand, chemical oxygen demand, phenols, cyanides, and many other hosts of complex chemicals. Ozone is a technology that's proven to deal with many of these complex chemicals. What is ozone? Ozone is when you apply electric charge to the molecule of oxygen, which has 2 atoms of oxygen. You break it into 2 atoms. Each atom will go and attack another oxygen one to make the O3, which is the molecule of ozone, which are 3 atoms of oxygen. And you see here the increase of the use of ozone plants in the United States. And here is the number of new and expanded plants using ozone. And you see the increase, over 300 plants now in the United States. And the volume is increasing, and the capacity has been increasing because of increasing population. Big cities in the United States use ozone. Los Angeles, Boston, San Diego. In Canada, we have Toronto, we have Windsor, and many other cities as well. In Japan is also, they're doing a lot of work in water reuse, and you see here the increase in municipal wastewater treatment. And here you see the different application of wastewater treatment and drinking water treatment in the years. In Canada, they are building now one of the big water treatment, wastewater treatment, additional treatment with ozone in the city of Montreal, which is one of the big cities, more than 1.5 million. It's close to 2 million now. And it is one of the cities that attracts many of the people from the Middle East, from North Africa as well. So ozone reaction, ozone is a powerful oxidant, reacts with the PPCPs. What are PPCPs here? The pharmaceuticals and personal care products, and EDCs, which is the endocrine disrupting compounds. And that is a key issue for the sewage because it has a lot of these compounds. And also, ozone will be reacting as a direct or indirect when you have the hydroxyl radicals produced. So the reactivity of ozone with target compounds is important because if we know we have certain compounds that we remove it, then, excuse me, you tailor your design to deal with that by when you know what's your pH, what's dissolved organics, what is alkalinity. So you design your system to produce certain amount of ozone to deal with that. And we did a project in between 2013 to 2015 in the city of Windsor, a sewage treatment effluent. We did a pilot plant at the sewage treatment plant. So we selected certain pharmaceuticals, and this one here, chlorotetracycline, and this is a typical tetracycline used in many applications, and in fluoxetine, which is the way you pronounce it, and that's also another antibiotic used a lot for animals. In North America, people have a lot of animals like dogs and cats, and also the farms. There's a big animal farms, like there are farms 1,000 cows or more. So they use a lot of these antibiotics. They put it in the water in order so the farms, so these animals, they don't get sick. And also the gemfibrozole, which is used typically for cholesterol issues and other compounds. And also we use some reference compounds in the study, and also we used ozone and hydrogen peroxide, which is the advanced oxidation. So we went, as you see, the concentrations highly pure compounds from the companies that produce it, and you see these are the chemical structure for that, and you see it's a very complicated structure. And the amount of ozone used depends on the molecular weight, on the chemical structure. You see the kind of bonds that ozone will attack in order to break it. So all these factors, you have to take it, and that's why you need to do a study to find out the rate of reaction to see what is that, and you see the ozone decay rate into the application. So when we did this study, and this Uslo, she's the postdoctorate, she's worked with us, did the analysis for the HPLC. And as I said, the University of Windsor was involved with this, and they had graduate students collecting samples and running the pilot plant and the sewage treatment plant. And so we had, and you see the amount of ozone dose is very small to break these compounds. And you see there is one, not all of them react the same way because of the structure of these compounds. And you see the decay when you increase ozone concentrations, and that is typical with the removal efficiency. We found that tetracycline has the highest removal rate compared to the other two. So this is good factor to know, to learn, and we've seen we increased the removal rate from the wastewater effluent from the CTC from 81% to close to 100% when we increased the concentration from 15 micromole to 35 micromoles. And the same thing with the others increased as well. So by increasing concentration, we are able to can achieve high removal rate. Another study done by one of our colleagues, Mr. Snyder, Dr. Snyder, Shane Snyder, he's now in Singapore at the Nanyang University, and he's the executive director there now at the present time. He used to be at the Southern Nevada, then moved to University of Arizona before he goes to Singapore. And he did that study when 2006, when he was still at Southern Nevada. And so he looked at also ozone and hydrogen peroxide, but he looked at a wider range. They had more money than we had to do the experiments. So they did bench, pilot, and full-scale operation to see the impact. Pilot scale is always the closest to the full scale if you want to think about of upgrading your system. And you see the data shows here, this is when these compounds, dilanthine and diazepam and DETT, and when you do ozone, ozone is more selective to certain compounds, and you increase the removal when you use hydrogen peroxide. Hydrogen peroxide uses only a small amount, 0.5 milligram per liter. And you see that's the difference when you use other technologies, they go 5 milligram per liters, but that will impact the water produced, because if you put chlorine, that will consume the chlorine at the end as well. So it's a problem when you go to the stream system. That's for drinking water or wastewater. And here you see ibuprofen. Ibuprofen is a common compound. We found it in wastewater all the time. And in fact, you found it in drinking water as well if you don't have certain treatment like ozone or advanced oxidation. So that, just to keep that in mind. And you see ibuprofen, and you see the amount. And when you use advanced oxidation, a slight increase. So you need to see with the reaction time. If you have reaction time about 20 minutes, ozone by itself is enough. And here, if you look at those compounds, there's a slightly more, but again, the reaction time help to achieve the same as advanced oxidation. But if you have a very short reaction time, 10 minutes or less, then you want to think about, if you use advanced oxidation, you want to achieve that, but you're adding another process. When you purchase hydrogen peroxide, there is a shelf life, you have pumping, there's also spills issues. So you have to think about all that from technical and financial reasons. If you want to increase 1% or 2%, the increase is not worth it of another process. I'm going to talk now more about the water reuse project in Qatar when I was there, 2015, 2016. We wanted to investigate the use from, in fact, from the first month I arrived, I put the proposal, like I arrived in April, in May, I put the proposal for that because I was thinking about it before I came, because you need to do a project that serves the community. And I've seen many projects is done not serving the community, because you have to think about this investment for research. It has to be a productive issue, and that's what I believe that treated sewage effluent reuse is important. So this discharge from sewage treatment plant is big there because there is a high water usage in Qatar, and there's a lot of chemicals of emerging concern, pharmaceuticals. The human body do not take all the pharmaceuticals used. You could use some of it, about 25–30%, the rest goes as waste. Where does it go? To the sewage treatment plant. If the sewage treatment plant does not have a system like an ozone technology, advanced oxidation, can break these compounds. If you don't have those, it will end up in the source water and comes in the drinking water. One of the main issues, the challenges is the pathogens. That's the biggest issue. Chemical emerging concern, pharmaceuticals, personal care products, PPCPs, and the PPCPs, that includes the PFAs that now everybody's talking about. And there is no system can remove it by itself. That's why we were proposing to do part of that to see what's the impact of removing these compounds as well. And if you need to use additional treatment process, that will be useful as well. Then this is the one here, the PFAs, which is the perfluorocatonic acid and perfluorooctane sulfonate. And those are used a lot in the as a personal care product, which we deal about, like what? For things for fire retardant issues, clothes, or also the even in the household we use non-stick pans and all that. All these things are there. So you need to look at all these issues when you do your research. Odor and color, that's a big issue in the wastewater as well. So why they are concerned? Because they are coming even in trace amounts, and we detect them in water, sediment, and wildlife, and drinking water. Because if you water your agriculture with compounds, pharmaceuticals, and endocrine disruptors, and personal care products, the agriculture, the plants will absorb these compounds, and you eat it eventually. And that is a problem. It's not coming from drinking water directly, but indirectly. So there are present in very low concentration, part per billion or part per trillion. Their compacts on human health is not fully understood, nor are the effect of complex, because we don't know when somebody lives in different places, what food this person has been eating, what water has been drinking. We don't have a data of 30 to 50 years. Different when you have the impact on fish and all that. The rainfall precipitation in Qatar is very low, and you have some sudden rain in December, April, heavy rain. You could have flooding because of that. And that is what you need to see how you look into that. So 2008 to 2012 in the Doha airport, one of the lowest percentages of long-term average taken between 62 and 92 in these 30 years. In 2012, the total precipitation was 23.9 millimeter at Doha International Airport. And it is only 32% of long-term average. And that's very low. This here show you the daily maximum temperatures per month in the year 2012. And you see the increase, a peak, July, August, like we've seen 50+ degrees centigrade in the sun. And so these are high temperatures. And you see, if you look at range of temperatures, it is increasing the period of high temperature. And you see here it's over 40. It's at 40 from the month of May, in fact, and and it's still in the 40s till which month? Till October almost, September, October. That's a long time, and that's a lot of evaporation. But, and I said it in previous lecture, evaporation doesn't happen only in winter time, in summertime, in winter time as well. And the sewage discharge, when it goes into like lagoons, there's a lot of evaporation happening there as well. Here we look at the annual precipitation at different years. 2012 was very low compared to other years. Water consumption in Qatar was in 2011, excluding 32.9 million losses from public water supply, that's leaks, used for construction, others. The use was 693 million cubic meters. Largest users were the private households with 295 million cubic meter, followed by agriculture 271, and government 75 million cubic meters. Commercial activities are lower, 29 million cubic meters, industries 21 million cubic meters. Agricultural sources were groundwater used 229 million cubic meter. Treated sewage effluent 420 million cubic meter, which is used mainly for watering the parks. Water use from the other sources here. So, and you see here private households, and you have agriculture, government, commercial, and shows here details. Mainly drinking water from desalination, public supply, desalination as well, the groundwater abstraction, and that is used, and you see a lot of farms using that, and you see some of the oases there as well using that. And I had an opportunity to go. It's beautiful areas and all that, but it's like in the middle of the desert, so they have oases there, and they get the water from the groundwater. So we designed a pilot plant, a modular pilot plant. What does it mean, a modular? That you could change the process, you could bypass some, or you want to add some additional treatment to see which one more effective at removing these compounds, and to have a technology, I call it a hybrid technology, to remove these compounds from treated sewage effluent to have a better water system. And we submitted, that was a US patent. I'm the lead in the patent, and I have two of my colleagues, but I was the lead inventor in the project. And the pharmaceuticals here are basically used for disease control for humans and animals. And the increase we use for animals has been dramatically in the last few decades. And you see by the production from the pharmaceutical companies. And the presence has been of these compounds known for many years. And many studies, we did that in many locations. We found that these chemicals are there all the time. So conventional municipal systems are not capable of removing these compounds. And they have limited success. And we compare, there are many studies that compare the removal with the conventional methods compared to using technologies like ozone reduction oxidation. One of the locations we looked at in the Great Lakes Basin, this is the 20% of the world's freshwater, and we found that there are officially 1,054 sewage treatment plants discharging. And you're looking at discharging from cities like Chicago, Detroit, Toronto. Chicago is 8 million people. And imagine the sewage discharge, how much? So that is an impact that needs to be taken seriously. And now there is a commission for water reclamation in the city of Chicago because of these issues that we raised. I worked there between 2010 to 2013 with the International Joint Commission, and we raised that issue. And in fact, we established a working group, and we developed 2 reports on this issue, addressing different locations and the discharge. So that is need to be done here, and that's why we bring this experience. We hope that we can do it. So what we, as I indicated, there is no one technology can remove all these compounds. So you need to involve different technologies, and that's what we did. So we include filtration and oxidation, adsorption, whatever we need. And these studies indicate that as I showed before, ozone oxidation of pharmaceuticals is successful. in wastewater and drinking water. So we need to implement it, and you could use it at a multiple location possibility. And that's what a modular pilot plant, you could add it in the front and in the end, and you see pre-coagulation or after. And we included the pre-coagulation as one of the treatment processes to reduce cost. So we used membranes, ceramic and polymer, and oxidation process. We use ozone and or advanced oxygen process, which is ozone and hydrogen peroxide. And the system is controlled by SCADA, which is computerized computer system. Basically, it measures the flow and the timing of the operations and controls the rate of the application when that is applied and the chemical addition when it's needed. This is the schematic for the pilot plant. What we did, the ideal is to bring sewage, treated sewage effluent to bring it, but we know there could be a problem. I anticipated that. So in my design, I put 2 additional tanks you can simulate a treated sewage effluent. And so what we do here, and we monitor turbidity, pressure, temperature, all that. So we can add ozone in the beginning prior to chemical addition. And also, this is here the coagulation. This is rapid mix. And what people say, okay, you could use reverse osmosis to remove everything. However, if you just remove it, but the cost of energy is quite high. This is a fraction of that. So you remove some of the compounds, then you go into just a regular filtration system, and you could add ozone again here, advanced oxidation process, and then you have more filtration system with membrane you could use in order to refine the application. This should provide a high quality water coming back at the end. And this is the reason why we include this, the simulation process, because if you bring sewage treatment plant, you have to have certain permission for classification because you're bringing a sewage effluent. So basically, we use regular water and we add chemicals to it to bring it to the level. Basically, the focus is not as much on pathogens because we know ozone has high capability of inactivation, so it's not the issue as much. But we use the chemicals we added, and also we put hydrogen peroxide in order to increase to reduce the pH when needed. And that is an ideal thing to use rather than using acid, much safer. And this is the built system, and you could see it highly sophisticated, nicely built. And this is the control panel here. You have control of the issues. That's some of the chemical additions, and that's the flocculation tanks. And we go to the other one. That's we see it from this side, and that's where the chemicals you add, and the other tanks to do that. And here you have a computer system to monitor this thing. As we said, it's you have a SCADA to operate, and that is where the oxidation reaction. And we did that for educational process, so we could use the system for education for graduate student or undergraduate. So when you put ozone and you see here the change in color, the change in particles shape, and all that, that will show here. And you see this is transparent surface. You could see through it in order to provide you with information. This will provide applications like for cooling towers. Cooling towers run almost all year long, you know, because of the weather. That will also reduce operation maintenance because they found that when they use chlorinated water, there is a corrosion happening in the cooling towers. Okay, they reduce the blowdown rate as well when you use, because if you use a treated sewage effluent without the additional treatment, that will be a problem because you have to blow down much faster, so more wastewater produced. Also provides sustainability for the system. So what the technologies we have, you have water quality, depends what kind of raw water, you use drinking water, wastewater, use secondary treatment, tertiary treatment, you can have a reuse from distillable, advanced treatment, and reuse. So each reuse depends what is the target applications that you're going to be using. You have to have planning program for municipal reclaimed water system. I see the time pass, so I'm going to move faster a little bit into that. The planning is a key issue because you develop strategies and you have some two different process control drivers for that. And you need to have also look at overall water resource management. And you have to have what we call integrated water management. And you go beyond just water supply challenges, but what's the demand, what's the change in the system. You have to look at different scenario. All the traditional practices of water management should focus on individual resources, the utilities. Also, you need to recognize the challenges happening for the water management. That's an impact on source water, improving the resource management. That will result in a more focus on broader water resources management, and that will improve the impact on the community and provide a more holistic planning method. The figure below I'm going to show you illustrate the difference between integrated and non-integrated water resource management. You see here traditional water management, which is non-integrated. You have water supply, the wastewater, the storm water coming in, the dry weather, there isn't any much. If it's a small amount, if it's a high, it goes down to receiving waters without treatment. What does that go to the water supply? So basically more contaminants here. When you come here to the total water management, you have beneficial reuse of storm water, goes to the water supply. When it goes to wastewater, again, we have the storm water, but here, receiving waters, you have to reduce flow from waste management practices, the BMPs. And even the wastewater, you have reclaimed water into that. So basically, that will reduce the impact on the source of the contamination. This project will result in determined environmental impact and also will significantly improve the opportunities to obtain benefits from water, regardless to the stage in water cycle. And the concept as integrating water conservation practice is important to reduce demand of fresh water. You see, this is typical what you have in a household. You can build a storage area for rainwater collection, and you have if you want to, that comes out to go into the what do you call it, some of the plants, but you have to have filtration here for the rainwater filter. So you could use that where for the discharge for the bathrooms and all that. And if you have highly treated system, you can disinfect it if you want to use it into other application as well. So basically, that integrated water system will better reuse, reduce reliance on surface and groundwater, and also you need to look at another list of management strategies: water conservation, reuse of wastewater, reuse of gray water, stormwater best management practices, BMPs, rainwater harvesting, enhanced groundwater recharge, increased surface water detention, dry weather, urban runoff treatment, dual plumbing of potable water, separate distribution system, multi-purpose infrastructure, and others. Green roofs. Green roofs is a bit difficult in very dry weather. but they use it in some cities, like in California, they're using some, and I've seen some in Ontario. So an application of that kind of approach was done in the city of Los Angeles in California in 1999. And basically they took a holistic watershed approach. And they received awards on the application for the quality. They completed in 2006, and they won many awards for reducing energy consumption, managing costs, and improved the quality. The project management planning, these items you need to look at: what quantity of reclaimed water, screen all existing and potential future uses, identify potential users, determine if users will accept reclaimed water, compare supply to potential demand, and prepare distribution system layout. Finalize customer list, determine economic feasibility, compile final user, prepare point of sale facilities, obtain regularity approval, perform on-site retrofits, and perform cross-connection tests, and begin delivering the water. What you see here, this is near Virginia area, and they have the system, and you see it here about reclamation of water and the system. So it is a good link, and you see a residence here, and you have pumping station, and you have the treatment plant and the storage area, the reclamation and storage area. And that's a portable. So basically, you could use the water for many of the purposes here. You see here, that's you start from here, you go all the way, and then you treat it again in order to, before you send it out, so you could use it in different locations. They went even for car wash treatment system in Brazil. And for example, you come the car, you wash, come down here. Here you could use a hand wash, or even the one with the machines, basically. And you have oil water separator here. And number two, because when you wash the car, you will have some oil coming. Wastewater reservoir here. And then it goes into treatment. Could have flocculation, could have a reverse osmosis. It depends on what system you have. Then you go to reservoir, then you use it again. So it's another good cycle. Excuse me. So in many cases, a reclaimed water distribution system will provide water to diverse customer base. Urban reuse customer typically include golf courses, parks, and may include commercial and industrial customers. Some cities in the United States, the reuse program provide water for cooling, wash down, toilets, flushing, and irrigation. Each water use has a distinctive demand pattern thereby. That concludes my presentation, and I'll be more than happy to answer any questions.
Thank you, Dr. Saad Jasim,
My pleasure.
for this very interesting and very practical topic, which is very important for all countries, because everywhere you have a problem of water use, and of course some country like Canada, they don't want to have it because they have a lot of water. So as I will give the floor to Salim, then I have to talk about in Arabic, but first Ustad Salim.
Thank you, Professor Ahmed, and thank you, Professor Saad, for this lecture. I think better to give a small brief in Arabic, so then we go for the question and answers.
Right. Thank you. So I will share the screen. Do you see my flyer?
Yes.
Okay. بسم الله ورحمة الله تعالى وبركاته. رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني. صدق الله العظيم. أريد أن أشكر الدكتور سعد جسيم رئيس الرابطة الدولية للأوزون، مستشار بيئي في وينسون Windsor, if I pronounce it good. تحدث عن إعادة استخدام المياه، حل لندرة المياه واستدامتها. من الواضح أن ارتفاع درجة الحرارة والتغييرات المتوقعة في المناخ سوف تؤثر على النظم الإيكولوجية والتنوع البيولوجي، كمثال واضح انخفاض مستوى المياه وتلوثها في بعض المناطق، وسينتج عن هذا انخفاض في الرطوبة والظروف اللازمة لمواصلة تطور بعض الأنواع الحيوانية والنباتات والكائنات الحية الدقيقة. ومما لا شك فيه ستكون تأثيرات تغيير المناخ على الاحتياجات الصالحة، على الاحتياجات للماء الصالح للشرب ومياه الري. وكما تعلمون يعني لأن عدد السكان سيكون يعني كثير جدا، سيكون يعني الماء بالنسبة للري سيكون كثيرا جدا. إذن خلاصة هذا أننا سنحتاج إلى مياه كثيرة. من جانب المناخ سيكون تلوث، ومن جانب عدد السكان سنحتاج إلى مياه عذبة للشرب وللري. جاسم، وأشكره، الخبير في معالجة المياه وإعادة استخدامها، وهو رئيس جمعية الأوزون من جديد، سيناقش في محاضرته التقديمية المشاكل المرتبطة بمعالجة مياه الصرف الصحي وإعادة استخدامها، ومشكلة البكتيريا المقاومة للمضادات الحيوية والتقنيات المتقدمة للتعامل مع هذه التحديات والحلول. إذن اليوم بعد المحاضرة الأولى واليوم هذه المحاضرة عرفنا كل شيء عن water treatment and reuse، يعني إعادة استخدام المياه، حل، والعنوان يعني يناسب هذا. الأستاذ الدكتور جاسم الذي درس كل هذه الأشياء في قطر، كنت معه كأنا أستاذ في الضوئيات أو توليد الكهرباء من الطاقة الشمسية، وهو عنده هذا المنهج، يعرف كل شيء، وإن شاء الله سيشرح كل هذا في المستقبل في دروسه في الجامعة الافتراضية. أشكره جزيل الشكر، وسأعطي الكلمة للسيد سالم لكي يفتح النقاش. سأغادر السكرين.
شكرا بروفيسور.
تفضلوا.
شكرا بروفيسور أحمد. Let's go now for the session of questions and comments. So please, anyone who wants to raise his hand to talk, you can have at the down there, you can raise your hand, and who wants to give a question in the chat also, we can say it. So everyone, welcome for your questions. Okay, so there is.
إذا لم يكن أنا في واحد ولا؟
No, here I have the Prof. Whom there? Yes, Dr. Abdel Ilah. He's asking about the presentation and the video. All the videos, it will be there in VLU in the YouTube. You can write day 1 VLU the opening lectures. You will get it in the YouTube. We are putting each lectures there, so you can go over it. And related to the registration, once you enter the lecture, it is automatically we register everyone. Related to the certificate, it will be after finishing, inshallah. the lectures, the open lectures. Right, Prof. Ahmed, you can have comments from your side or
yes. Thank you very much. Dr. Saad, you are dealing with ozone for the treatment of water. The first question is there any other method to do exactly the same at low cost? Or let's say, can you make a comparison of all methods what we have actually as state of the art and the cost, the technology, the how it's how you deal with this stuff?
In fact, there were studies comparing cost of operations, and my colleague Shane Snyder, he did quite a study on this back when he was in Arizona, and ozone shows that it is one of the low costs for operation when it comes to treatment processes. I'm going to try to get you a slide to show that. In fact, there was also a study we did in 2020 was published on the cost of ozone, and it shows ozone application has been reduced dramatically in energy use compared to others. And in fact, the process that is the studies that shown before, it shows that that ozone cost is lower than membrane and UV as well, almost the same as UV. However, UV by itself does not remove the pharmaceuticals like ozone does. So you have to use high level of advanced oxidation process, which is between 5 to 8 milligram per liter of hydrogen peroxide, and compared to about 10% or less of the use of for ozone. So it's a very low concentration. So the cost will be less. There is also the size of the application will be less because you don't have to have additional big treatment processes or storage area. You can use ozone by itself to deal with with that compared to as I showed into the treatment when you use ozone or ozone and peroxide. Depends on the removal, and you have the contact time. You could achieve a slightly higher contact time. You could achieve the use of ozone by itself only. And however, there is no technology can do it by itself. That's why I use the term of hybrid technologies, which is the use of different. So I used ozone, and I used ozone and peroxide, and it depends my target compounds, and I use membrane as well. So there are different technologies used combined, because still the cost of this operation will be lower compared to many typical and basically you reduce the demand on the resources as well. So yeah, so there are other things, and it depends, as I indicated, what kind of things you have. But the use of ozone has been very successful. You go to Singapore, the use of membrane and ozone together also for the drinking water supply, the reuse. So as I indicated, it depends on what is your target. You can do that. Ozone is one of the low cost now considered, because you achieve many other goals, not one.
Okay. So if there is no other question, I would like to continue, because it's very important. You know, in Morocco, most of the countryside, they wait until the rain is coming, And in Morocco, because the climate change maybe, the rain is not always there. It comes at once. And people, they collect water in a kind of, I don't remember the name, it's a tank, and they drink this water the whole year. They don't treat it. And I think it's a very good solution, because you show in one picture in a house that one can treat the water before it's coming inside to the kind of save. And it would be interesting if, for example, you can suggest a kind of engine that can be. That's why I ask about the cost, because in the countryside people are poor, they don't have that much money, and I wonder if there is any possibility that these people get a kind of tank that's when the rain come and they have a lot of water to be treated, and then they, instead to drink it directly, they drink it after treatment, because nobody know what's happened when they drink this kind of water, which is can be very somehow toxic or with bacteria, etc. You know what I mean?
Well, the issue of each site, it's quite specific, and so depends on the location, the water source, all that. Like if it is rainwater and collected, in a good way without contamination, the treatment wouldn't be complicated, and you can do that. But the thing is, as well, if you store it, that's another case as well, because you have to think about, if you put, for example, water, clean water, treated, and you add chlorine to it, even after the treatment, you have some of the organics. When you put chlorine and you try to store it, you would cause some of disinfectant byproducts, and that increase with time. So that is that could be an issue that you have to estimate what kind of the time is needed, and so it is all things you need to look into when you decide on the treatment system. But as I said, with technology and the will is an important thing, because people, if they are willing to do something, and with the presence of technology and funding, I think it is always possible to achieve good quality of drinking water. And for the reuse is the same. If you how can I say, if you implement a good treatment system, and knowing that what kind of problems you have in the water, you can have a good treatment in your system as well.
Okay, thank you. Thank you very much.
Thank you, Professor Saad. If it is no other questions, I think if you give us the
So
there is one question in the chat, I guess, how it could be.
There is a question here.
Yes.
From Mr. Abdul Samad. Is there any specific, I think
ozone gas here.
Ozone gas, okay. A specification to produce best results, to remove odor. Is there oxygen, is an oxygen generator will do the same result? Well, it depends on the, basically, ozone is ozone. It depends on what concentration you need to use. Ozone is used successfully for odor control. There are studies done basically in many places. We did some, Los Angeles did a lot, and odor control is a big thing in drinking water. We used to have that in Windsor, Ontario. When I arrived in Canada and I went into Windsor, summertime, I arrived in winter. There was a smell of the like an organic smell. So they start using activated carbon, powder-activated carbon. But that is a hit and miss because they can't put it all year long because it's too expensive and produce a lot of sludge. So when we started using the ozone, after that, that issue of odor and taste was completely gone. In fact, 4 awards of best tasting water was reached, was achieved for the city of Windsor for that. Yeah. And any ozone generator will produce ozone, but as I said, you need to know its concentration.
And he's saying also how it could be compared with the UV light.
Okay. UV light is basically has specific applications in disinfection. And UV light does not get impacted by cold temperatures. Ozone does. So you need, that's why when we calculate the ozone for an activation, we need to look at temperature, and there are tables. We have a regulation, a guideline called the CT, which is concentration and time. And also we implement the design of the system. So basically, when the temperature become cold, ozone concentration need to increase. And there are tables from 0.5 centigrade degrees centigrade to 25 degrees guide people to what concentration. UV light works, but UV light does not remove odor, for example. Taste and odor does not do that. You have to put hydrogen peroxide with it. Hydrogen peroxide and UV, and I have a publication study comparing ozone and peroxide versus UV and UV and peroxide. When you put the peroxide with the UV, for example, for the pharmaceuticals, you're going to impact the chlorine and distribution system. You have to add 3 times the amount of chlorine because the high concentration of hydrogen peroxide will react with chlorine. It will basically neutralize it, oxidize it, work with it. So basically, you remove it, you have to add amount. But that also produce trihalomethanes. And the paper we published 2012, it shows that trihalomethanes, which is disinfectant byproduct, increased by 4 times. So each application has its, a lot of applications of UV is for treated water, for UV, for groundwater that has low turbidity, low hardness. So you have to have, because if you have a cloud or hardness, basically the UV will not be applicable. So there is challenges. There is no silver bullet. But ozone has, and ozone showed that when you use it, for example, for the pharmaceuticals, even with peroxide, is more cost effective than the UV with the peroxide.
Okay. There is a question from Dr. Abdelilah Bergani. He is saying electrocoagulation could be a more environmentally friendly method. So why it is not used in sewage water treatment?
Well, we did some study. In fact, we published it a year ago on the removal of arsenic and manganese from groundwater by electrocoagulation. And so the thing is, there is always a challenge when you have that, because the potential accumulation of when you have wastewater on these plates, on the anode or cathode, so basically it loses efficiency very soon. So you have to have continuous cleaning for them. In the beginning it works, but then start to deteriorate quickly. And then basically you just settle these compounds. You don't oxidize it. That's a difference. Ozone oxidize it. When you put these compounds, and that is typical when you have the waste, you move it basically from one location, you're going to put it in the landfill. With rain, it's going to bring it back to the water table, groundwater or surface water. So basically, but when you oxidize it, you reduce remove the toxicity and impact on nature, on environment, and on human health.
Okay. Thanks, Prof. Saad. Is there any other questions, please? Right. I think Dr. Ahmed, do you want to comment, or just we finish the session? Just before finishing, Professor Saad, thanks from all the participants they sent to you. If you conclude your session with the brief related what you said.
It's always a pleasure of mine, and I look forward to teach that course into the for the virtual learning university. I think it's a big opportunity for the MENA region to have this application, and we have the pilot plant. We could investigate any potential use for that.
Thank you, Prof. Ahmed. Ending the session.
Yes. First, I want to say something about tomorrow.
Yes, please.
So allowed me to share again my screen. This is the old one. Just a moment, please. Oh, what's going on here? It's fine. So I take it out. Then I will open another one. It's running. Okay. So tomorrow is Friday, I guess. That's the day 12. And we October 29, 2021. At 11, if everything is working properly, we will have Professor Thomas Hannabel. He's a colleague from former time when I was director in Helmut Center, Berlin. So he was also in the center as a student and as a postdoc. Now he's a professor in Germany, in Illinois University of Technology, not far from Berlin. And he's one of the successful guy on artificial photosynthesis. This means he tried to imitate the photosynthesis in real time in the lab. And he was able to make a he used semiconductors, tandem solar cell. I will talk about it in my talk about this. And he is one of the world record worldwide on this. And he will talk about, as you know, artificial photosynthesis is a process, electrochemical process, where you can make power to X. You can produce green hydrogen, you can produce methanol, you can do a lot of things. And he will talk about this very important topic, which is a topic of the future. So it will be at 11. I contact him this morning, but I don't find him since he's outside Germany. But because I know this through WhatsApp, the time in Germany is not the time that I saw in WhatsApp. But he will answer, and tomorrow we'll have his talk at 11. Then, if you allowed me, on Friday, on Saturday, sorry, it will be one talk from me, and I will make a kind of very overview of photovoltaics. It's photovoltaic, power to X, solar fuel, building integrated photovoltaic, and digitalization, the title. So I will develop all this stuff, starting from the nature, how the nature is working, and then going forward to explain to people everything about photovoltaic, to power to X, etc., to the use of panel in the building, etc. It will be my talk on Saturday, the last day of our online lectures. Of course, the same day I just discussed with my colleague Evan Gordon. He also, if you give me just a small break to find his talk. So Gordon here. It will take a few seconds and then I'm there. So here. So Evan Gordon, he's the editor-in-chief of Solar Energy Material and Solar Cell. This is a journal where I am also in the editorial board, and he's the editor-in-chief, and he will talk about status of crystalline silicon. Professor Evan Gordon, he's very well known. He's manager of photovoltaic technology and energy system at big institute in Belgium, and also he's professor of digital photovoltaic at Detlef, that is in Netherlands. So he will also be with us the same day, this means Saturday. He will give a talk, I think at 2 p.m. So I will be at 11. It will be a huge discussion, very interesting. I will also show video about all my former institute and what we have done, etc. It will be very exciting. And then come Evan Gordon. So that's all what I can tell you today. And I want to thank the audience, to thank Ustad Salem, to thank Saad Jasim for this very interesting day. And I wish all the best for everyone. Thank you.